I hate PowerPoint. So I either like essays, which we had one printed out, which is a proposal that I got asked to write for NSF this summer. And in fact, the reason I'm here is that proposal got funded against all odds. You'll see why if you read it. And so we're prospecting around for smart, interesting people who might want to help us do this project. It's a large project. It's $2 million a year for 5 years. NSF balked at the $2 million. They only funded $1 million a year for 5 years, but managed to find the other $1 billion. So we're really going to do it. And as I go through this thing, you'll see that this proposal is somewhat far-fetched. The way it happened is that we talked about this in my research groups off and on for decades, and always something else to do. And about a year ago or so, two things happened. One was that Peter Freeman was starting to fund the Genie reinvention of the Internet, and I got asked to be on one of the committees to talk about it. And I remember sitting there thinking, geez, the Internet actually was probably the best thing that my research community did in the 70s. And if we're going to reinvent and redo anything, it should be programming. And so I started thinking a little harder about that and realized that it would be awfully difficult to reinvent programming since we're sort of been embedded in pretty much the same paradigms for pretty much as long as I've been in computing, which goes all the way back to 61. Take Simula as first appearing in 64 and 65 or so. Then the stuff that we're doing today would not only be all too familiar, except for the networking. A lot of the best people in the 60s would think what most people are doing today is kind of retrograde. And in any case, it is extremely recognizable. And so once you've been embedded in something for that many decades, it actually sets up a sense of normality. So you have the sense of what's normal to think about, what isn't normal to think about. If you're doing it for so long, it's actually hard to think really varying thoughts. So the other thing that happened is that one of the researchers in our research institute, Ian Piamardo, who has been interested in the sort of now kind of distant topic of bootstrapping from nothing for the last bunch of years, actually started showing some real progress on his latest system about a year ago. And as I move into what this proposal is all about, which is basically to take a very large computing experience and do the entire thing from the end user down to the metal in less than 20,000 lines of code. One of the things that everybody here is quite familiar with is you can use up a lot of those lines of codes as bottom. And so you have to have some strategy to deal with the issues at the bottom. You can use up anywhere from 1,000 to 10,000 or more lines of code just on TCP/IP. And of course, we have to do TCP/IP in order to do this, and you can't really spend more than a few hundreds of lines of code to do one that actually works well enough. And so, I guess the other introductory remark here is that when I first prepared this particular talk, I gave a version of it a month and a half ago at NSF, and I realized that my usual approach, which is usually critical, that is, a lot of the things that I do and most people do is because they hate something somebody else has done, or they hate that something hasn't been done. And I realized that informed criticism has been completely done in by the web, because the web has produced so much uninformed criticism is kind of regression's law. Bad money drives the good money out of circulation. Bad criticism has driven good criticism out of circulation. You just can't criticize anything because it's immediately tagged as a rant, no matter what's behind it. And so I've changed my tune and tried to shift over to asking questions rather than criticizing. So this talk will be successful if I can get you to read that paper and get some of you to contact me. So I had to rewrite this story, but I think it's a good story about our profession. It's full of emperors without any clothes, but of course in the original story the kid declared that the emperor had no clothes, and that was a direct comment and criticism. It changed the question. Doesn't the emperor have no clothes? And it's interesting that my neighbors, who are not computer scientists, just have questions like this that they ask all of the time. And trying to think of something reasonable to tell them. Why does it take long? Why is there less room? My wife just got a huge top-of-the-line Mac palette book, the biggest of everything. And it ran slower than the one that she had. And discovered it's because even though the disk drive on it was larger, she got the largest one, there still wasn't enough room for all the caching the system was doing to make it appear as though the system had been written in some reasonable way. In fact, the system was unbelievably inefficient and needed enormous amounts of disk space just to get by. Of course, that's true of Microsoft establishment also. No, that was a criticism, sorry. After an update, why do I have to reboot my machine? That's a really good question, because you would think that things would be more lately bound after all of these years. And yeah, can do WYSIWYG authoring in Microsoft Word, which was originally done back in 1974, but for some reason I can't do it in my blog or my wiki page, which came much after. And in fact, I can't even really do much authoring in this most useful browser thing, even though HyperCard was already 8 or 9 years old by the time the browser came on. So what happened? Why didn't somebody just put HyperCard into the browser instead of Apple? I mean, instead of JavaScript and infamous DLM and so forth? I think everybody here knows the answer to those questions. I hope you do. If you don't, talk to me later. I have my own versions of these questions. So pretty much any of the computers we have today has pretty much what the total computing and storage capacity of the entire internet was around 1986 or so. It's interesting to try and figure out exactly. But the internet already had zillions of nodes. It was already going and working quite well in the mid-'80s. It was very simple then. It's very simple now. But what happened, what's inside, when I look inside the PC or a Mac, is I don't see anything that's like anything. I don't see any scalable architecture in there. I'd expect to see thousands of virtual machines. But in fact, talking to my friends at Microsoft, they say rarely does Windows XP ever have more than 20 processes going on in users. Yeah, think about that. Because the internet has been able to scale by 12 orders of magnitude. So there must be a reason. As a systems person, I'm really interested in scalability. And I'm interested in how the system software on these computers hasn't scaled. I'm interested in how the internet has scaled. Especially since you could throw away the operating systems on all of these machines and essentially just get rid of them. You could have an internal internet that would do everything an operating system does and would scale. And et cetera, et cetera. And so I did a little calculation. here. I love books, and I have a collection of Encyclopedia Britannicas, and my favorite is the 14th edition, the classic one, and each volume is about 1,000 pages long. It's about 1.5 inches thick. It's printed on fairly thin paper. And if you stack those up, you can sort of read for yourself. 11,000 volumes of 1,000 pages each. So many pages and so many lines of text. And actually, if you start counting lines of code in just the operating system and Windows applications, so forth, you get to quite a few lines of code. Probably more than this. Now, this comparison is completely unfair, so I put apples there. Down here is this system I'm using to give this presentation, which also is its own operating system. In fact, it was its own operating system back at Xerox PARC. And everything being done here is being done by the system. We're not using any Windows code at all. It has its own internet sockets and everything. And it's about 230,000 lines of code.
So this is not PowerPoint?
This is not PowerPoint. And
you said you made it PowerPoint.
yeah. So just to prove that, it's not PowerPoint. So it's actually everything is dynamic and alive. There are no modes, there's no editing. That's kind of what we were thinking about 30 years ago. And so one of the things that we've done over the years, Squeak is only about 10 years old. It's just a small top name because we feared Java wasn't going to really be compatible across machines back then because of the way we implemented it against a standard with tests to see if it performed the test standard. That has never produced a completely compatible system. So the way we used to do it is to make an actual model of the virtual machine in high-level form, debug that, and then write a translator to translate to any several dozen platforms. So this system, I'm not extolling the virtues of the system. This is an old, obsolete system that reached its high point around 1978 or so. But this system does run bit identically on dozens of platforms. And if you're going to be on the internet, you kind of have to run bit identically. Just because otherwise, who knows what's going to happen. So, in thinking about the functionality here, we did a little test that indicated that pretty much all of the time we're only using 100,000 lines of it. And we started wondering about, well, how small could you make it if you didn't do it in 1970 small talk? Like, what if you actually tried to use some higher level ideas to do it? And various hand waves got us down thinking, well, it'd be interesting to shoot for 20,000 lines. Now, of course, we never intended that we were going to do this, because who would fund this? Nobody today. And it might even been hard to get ARPA back in the 60s. But we thought 20,000 lines of code would be pretty nice, because that's about a 400-page book. And boy, one book is different than an encyclopedia, and one encyclopedia is different than an Empire State Building. That's because our brains don't scale. The only way we can scale things is not by size, but by abstraction. Everybody knows that. In fact, there's nothing in this talk that's going to say that you don't already know. And then we thought, boy, 20,000 lines of code, that would be really interesting. What if you could also explain it? And you wind up with something about the size of my favorite book, which is the Molecular Biology itself. It's actually a molecular biology book about computing. And this book is one of the great books of all time. We do not have an equivalent book in computing. Really a shame. One of the reasons is that the biologists are incredibly fortunate in that nature has already presented them with living things. And what they spend virtually all of their time thinking about is how those things work rather than all the different other ways you can make living things. Right? So all they have to do is nail it, get a couple of geniuses to write 5 or 6 editions of this book, and you get this masterpiece. This book doesn't even require you to know anything about chemistry to start reading it. Just open it up, start reading it, and it just takes you along, and you get to the end of the thing, you know a lot about molecular biology. Because it was not a lightweight book, it was just extremely well done. So we started thinking about that, and I wrote a white paper, as I usually do, just to try and think it through. I never finish these white papers. But I hand them out to everybody. And so an amazing thing happened is that this summer, NSF called me up and asked me if I would try and turn that white paper into a proposal. I still don't know exactly why. This is not really their cup of tea, because there's a high probability of failure. In fact, the difficulty the reviewers have with the proposal is that you'll notice when you read it that it actually has sections in there where we say we don't know what we're doing on this part. And that used to be okay a long time ago because that's what research, the difference between research and engineering. In engineering, you're supposed to get that jet engine working and not have the plane fall out of the sky, whereas in research, you kind of want it to fall out of the sky in some interesting way. So then they surprised us by funding it. And this is part of our kind of grand challenges list that we think people should be doing. And one of the most interesting things that I think, everybody in this room, this talk is so full of cliches, I can't stand it. But, there just hasn't been a Moore's Law for software. Just incredible. Yes?
Yes, it has. It's got progressively slower.
Yeah, it's the inverse Moore's Law. Maybe the inverse square Moore's Law. So that's an interesting one to think about. What would it mean to do something that's around 2 orders of magnitude improvement? It's hard to even imagine what that would be. Interoperability. I just can't believe, criticism. It would be great if we had interoperability. And I've always been pissed off that the vendors aim personal computing at business, where you have the least enlightened, least interested in computing end users, the most boring people you've ever met. And of course it's boring. But it's really bad because the people who should be joining our field and should be having fun in our field fail to see the fun. In fact, we realize now that we've been analyzing the English language wrong, but the suffix "ding" actually is a negation operator. So fun ding means no fun. You're talking to people who don't know why this stuff was done in the first place. And these last two I won't bother explaining what they are. They're really critical. So one of the things some of us old people decided to do is to take matters into our own hands and try and make a difference. So Meeker Ponte and I and a bunch of other people decided to do this $100 laptop and just, by God, do it on the grounds that all the laptops are made in Taiwan anyway. The world's largest laptop manufacturer is Quanta. Makes 43% of all the laptops in the world, including all of the Hewlett-Packards, all of the Dells, most of the Sonys, and half of the Macintosh laptops. They just have a different factory for each one. They also make displays. And Nicholas talked to the CEO of Quanta with the following wonderful proposition, which involved showing this guy how many hits the $100 laptop was getting on Google, how few hits this guy was getting on Google. And so the wonderful end of the story was that not only did this guy agree to build this $100 laptop, he actually put in a substantial amount of funding to help do that, including enough funding to do the remarkable display on this machine. So it's less than 2 years since this project started, and the first 1,000 factory-built machines just appeared last week. I came within a couple of days of being able to give this talk on this machine, which I think would have been fun. And in order to do a real computer for the cost of a little over $100, one of the things you have to do is solve the display problem. And the CTO of One Laptop Child company is an extremely talented lady scientist who used to work for Intel, but was a specialist at doing displays, and she had the guts to actually design and really invent a new kind of flat screen display as part of, imagine putting that in your critical path. And this display takes 1/7 the power of an ordinary display and costs 1/3 of an ordinary display, but it's 900 by 1200 resolution. It costs just about $39 or so, and it can be used in the sunlight and also backlit. So it's a real breakthrough. It just shows that 15 or 20 people who are determined can do pretty much anything. Although I hope that Nicholas gets the Nobel Peace Prize for this, because he was able to manifest this thing out of almost nothing. Being able to get buyers for the machine, being able to get funders for the project, get builders for the thing, and it's actually happening. But of course, a children's computer is not the hardware, it's the experience that's on it. And that is a different matter entirely, particularly when it's going into the third world. But I'll leave that aside. So these are things that affected me deeply when I was younger. And essentially this project is looking at the physicists with envy and saying, geez, every time the physicists do something, it starts out messy, and then they wind up inventing some mathematics that makes it look really pretty. And it usually fits into an eyeful. And if it fits into an eyeful, you can actually notice things about it that are hard to notice if it's 10 or 15 pages long, like certain asymmetries between the electric and magnetic field, which attracted Einstein's attention that probably shouldn't have been there. And this is my Bible when I was a biologist, and I particularly like this. This is the Constitution of the U.S. And if you think about it, it's the kernel, you can think of it as meta-programming if you want, but it's the kernel of an operating system that's been running with millions of not terribly cooperative parts, namely us, for hundreds of years and hasn't broken. Think about it. Meta ideas here, they had to be small in order for them to work. Those guys really knew what they were doing, and astoundingly, everybody who worked on the Constitution of the United States was actually educated here, something which might never be possible again. So, when I started in graduate school, Ivan Sutherland had already done Sketchpad, which used a kind of a field idea, which I'll get to in a little bit. And the big topic of conversation 40 years ago was the ARPANET, which hadn't been done yet. And Licklider, this guy, called it the intergalactic network, even in his reports to the military. And the reason he used that term is that he was convinced that networking was bad in the 60s because people weren't thinking big enough. They were always trying to solve little problems, particularly vendors like IBM. And the vendors were trying to build perfect little machines that were half duplex rather than full duplex and so forth. And when I started in graduate school, the publications of Simula in this country had just come out a few months earlier. And it turned out all three of these things were abstractly similar. This had a thing that wasn't called objects in it, but that was the way the graphic system was organized. This had separate things that were supposed to cooperate in some form by sending messages. This was designed for huge oil refineries and Norwegian shipbuilding. And my background was, I had a math major and a biology major. And these things just all looked very, very similar. They looked like a network of computer-like things just sending messages around. It didn't matter whether it was hardware or software. And I thought, boy, we have 100 trillion cells in our body, and it only took 40 cell divisions in order to make us. Actually, it takes 50, but 10 of those cell divisions are actually used up in debugging and destroying cells. It's one of the nicer things that nature has given us. So this became kind of a mental image for the systems, and pretty much everybody in the ARPA community also felt the same way. And there was also a computer done by this guy, Bob Barton, that had the structure in it. So this computer, the B5000, had 7, for my money, had 7 out of the 10 best ideas ever done in software, put in the hardware of the machine, designed in 1961, happened to be, by luck, the third machine I ever had to learn. And it's be quite recognizable to people today because every byte-encoded VM on the planet is a software version of what this machine executed directly. Right? So this was the first computer and almost the only computer where the designer of it said, you know, people are going to write in higher level languages. So let us make a piece of hardware that will optimize that. Instead of, think about what we have today. We have everybody trying to write in higher level languages, and yet we have to emulate the hardware environment they should be running in because the computer chip vendors refuse to learn anything about software. So just think about how out of whack this is. And the other book I carry around is this, because the bottom half of page 13 had the other part of the question. So if objects are the way to organize things, how do you organize the methods? And one of the ways of thinking about it is to think about it in the self-referential way that McCarthy arrived at. And of course, there are zillions of universal Turing machines before McCarthy did this. The interesting thing about what McCarthy did was it was the first time anybody had done a Turing machine that had slope to it. So it was not just universal, but it was actually within some short Hamming distance of whole bunches of interesting computations. And yet it was still small. So that says something interesting. So I've always thought about this as the Maxwell's equations of programming. Right? And of course, what we need now is the relativistic equations for programming, whatever that means. So the other thing about the ARPA community was it had big ideas. It wasn't just the group of us. We were part of the ARPA community, but we were by no means, we wound up getting the better books written about us. But in fact, the ARPA community itself thirsted after this notion of being able to provide people with a kind of an amplification of their intellect, an amplification of their intellectual reach, both in time, in space, in ideas, and so forth. And so this whole community cooperated and talked with each other very well. And one of the key parts of it was this early workstation or first workstation called the ALTO, which besides having the screen on it, it was about 50 to 100 times faster than you could get on time sharing. So all of a sudden when you sat down to this machine, you were sitting down to something that was a bit like a supercomputer, and immediately you found that there are a zillion things you could do without optimization. So you could go out and drink a pitcher of beer at lunch and do 5 or 6 complete experiments before supper time because you had this machine and you didn't have to optimize. You could just throw the code away. You write these short little snippets of code, and since most ideas are mediocre down to bad, the whole idea is to be able to have lots of ideas and get rid of most of them. So this is a perfect setup for that. And it's interesting to look at the specs here. So clock speed today is times 75, bandwidth is times 150, 11,000 larger main memory, disk is out of sight, 10th the price. But if you look at Moore's law, it's 23 doublings since then. So that is a factor of 8 million. And, you know, no matter how you twist and turn this, you can't find 8 million in there. Something is not scaling. And my favorite guy to be critical is Butler. So he has the harshest thing. I've usually been the harshest, but the benchmarks that we did show about a factor of 600 has been lost. And Butler has pretty good figures that show a full factor of 1,000. Now think about that. That's 10 doublings. Right? And the doublings happen every year and a half. Right? So that means 15 years has been lost because of bad architecture. And so there's this myth that says, don't do special purpose hardware because Moore's law will always overtake the special purpose hardware. Bullshit. That's not even close. Actually, what's happened is we've lost a factor of 1,000 in efficiency because we can't run the code the way we want to, the way it needs to be run. That's a really interesting figure to go back and look at. So another thing we tried to do at PARC, which I'm not going to dwell on much here, but we just noticed that the thing that was most like the user interfaces of the 60s was a nuclear power thing, or maybe a nuclear submarine thing where it takes 20 people to run the application on it. And in personal computing, you really can't have that. You really need to have something that's explorable, undoable, something in where the main thing you're trying to do is not so much functionality, but learnability. Basically taking the idea that if there is going to be progress, then you have to somehow build in learning into the thing, because no great idea that is put on a computer that is not learnable is a great idea. Right? It ain't there. So we saw this as a huge switch, and without trying to be critical about today, I would say today's user interfaces, even on the PARC models, are way too much like this. People actually take training courses for them. So one of the things we thought that would be neat if we did this project, since it would be so small, it would be interesting to try and think of it also as a museum on itself. What would that mean? So it wouldn't just be reflective, but it would actually be introspective. So it would actually not just be a model of computation, but it would actually have a model of itself. And so that suggests a rather different kind of user interface yet to be designed. So I think architecture is the key here. Again, I'm not saying anything people don't know, and I'll just put up 3 pictures here. Most software today feels like this to me, because once software gets beyond a certain size, you can only add around the edges, right? It grows by accretion. You can't really do much of anything else. And over here, we have something that nobody in computing knows how to do, what I call real engineering. Empire State Building was built by less than 3,000 people in less than a year. They had to demolish the old Waldorf Astoria Hotel in order to do it. The steel arrived from Pittsburgh, still 110 degrees hot, and the framing went up at the rate of 2 floors a day. Each floor of the Empire State Building had a narrow gauge railroad on it, and it had 3 times as many elevators going up the side just to get stuff up there than the building has today. It was one of the great building jobs, and anybody who has pretensions to be an engineer should get any of the 4 or 5 marvelous books, including a foreman's notebook, which has been reproduced in facsimile, that had little snapshots that this guy had taken in an old Pica typewriter talking about what was going on. So I claim that nobody in computing knows how to organize 3,000 people to do something really big and get it done in a year. So whatever software engineering is, it isn't anything like modern engineering. Software engineering is more like that, like architecture before there were arches. I think the best practice is rather more towards the pyramid. You could call this a form of dynamic object-oriented programming, or pick your favorite architectural thing that just isn't brick-like. And yeah, you can build big structures that are the size of this thing with 1/1,000,000th the amount of materials. But if you think about how primitive the best stuff that's done today is, it's appalling. So, my favorite Don quote here is, "Beware of bugs in the above code. I've only proved it correct, not tried it." And so what we have is a new kind of mathematics. Right? Old math is tiny little theorems that have an infinite number of instances. And what we do in computing is things that are finite but huge. Huge beyond the worst nightmares of any mathematician. And so we don't get to prove anything interesting. Peace to my theoretical friends, but essentially proving something is NP hard is not interesting, because you can still build it. You can build anything you want. So the real question is, how can you build it and debug it? And this is what makes this talk difficult, because I'm used to giving talks about stuff that we've already done. But here's an analogy. I won't play the Tacoma Narrows movie, but I love this movie. But everybody here has seen this movie any number of times. It's just a great movie. It's wonderful that the person who predicted that the bridge was going to go down had predicted it more than 6 months ahead of time, and had predicted more or less the magnitude of the wind, a wind that nobody thought would ever happen, 95 to 100 miles an hour. And so 6 months or so later, they were measuring a 95 mile an hour wind in the Tacoma Narrows. And so they actually went to the camera store. This is online. You can go to the website of the camera store that they got the movie cameras, and they just set the movie cameras up at the end of the bridge, turned them on, and just let the whole thing happen. Just so great. But, so to me, computer science is a science that requires an artifact to be made. So this project is partly to make an artifact that can be actually studied. Now the problem is 100 million lines of code can't really be studied. So you have to make something that's actually studyable, but it has to be big enough to be interesting. So we decided to take something that we understood and just try and, like this chain of being up here from tiny little building blocks to more and more complex architectures of things. So this is at least my favorite slide. And it's interesting, in my lifetime, people were right around there. This is Linus. I was born when Linus Pauling did his book on the chemical bond in 1940. And I was 13 when Watson and Crick did DNA. And we're now up to still thinking there might be a miracle or two in intelligent behavior. But all the ones beforehand have turned out to be architectures of things. So for this system, we've got basically something that goes from the power supply up to the end user. And we really have to do all of these things. And we're going to leave some of the logic gates alone, but not all of them. Because not just the temptation, but the things that can be accomplished by using field programmable gate arrays is just too great. Right? The thing that made the Alto interesting at Xerox PARC was the microcode. The microcode allowed you to make an emulator for a desired virtual machine that would keep main memory busy. And that meant that no custom-made hardware could run any faster. The thing was memory bound, period. And field programmable gate arrays actually allow some really interesting thoughts. And as you'll read in the proposal, there are about a dozen principles in there. I believe every one of you knows every single one of these. Maybe there's a couple that have escaped you, but basically there's nothing here that is particularly remarkable. And in our diagram here, essentially this middle area is the area that we actually don't understand very well. It also is the place where the most interesting ideas in this system, if they are going to appear, are going to appear. And we know something about how to do this pretty well, and we've done a lot of experimentation up towards the end user side. I'm going to give you a couple of examples before we quit and have some chance for some questions. So now we did this system called eToys for children, and while we wanted to make it really simple, and while we were doing it, we thought, well, we can toss a few more things in there that the children may or may not find, but we can try out some of our pet theories. So basically, one of the inspirations for eToys was thinking about, well, what would a hypercard on steroids be like? What if it were just had a really powerful, simple object model, and it was universal, and okay, so a little car that a child might make and makes it into a thing, and I can, like I did before, I can drag out some tiles here from the viewer on the car, and I'll just start the car going. Now, we saw that there was a little halo of stuff on that object, and here's another thing that's on a photograph, and so I could possibly drag out something on it. And here's another object, which is the script, but it's also got one of these things. So maybe I can write a script for it, and I can come over here perhaps and grab onto the thing that's there like that. And actually this whole thing I'm in, this world guy I'm in here, I can look at it. And so one of the ways of thinking about this system is, instead of having a class object and a zillion subclasses, it only has one kind of object. So this is a universal object idea, and the objects have different costumes. And to give you a kind of a sense of this, I'm going to suppress all the graphics.
Yeah.
And this helps you see that all of these things are actually the same. This idea goes back a long ways, because when we're doing the Alto at Xerox PARC, one of the thoughts we had is, wow, to a naive user, everything on the Alto is just a smart rectangle. The windows are rectangles, the characters are rectangles, and there's some sort of function and magic behind them, and that should allow you to make a different kind of object system than the one that Simula thought about. Now, of course, I have to remember where I did this so I can change this thing back here. Okay, so I'll just show you a few more examples. So the basic idea here, what I'm trying to convince you, is that the media part of this system is just endlessly recursive. In fact, one of the things that I forgot to do here is to show you how this presentation was made. So this is an idea we could never convince Apple of, but at Xerox PARC, we had unlimited desktops. And the reason was that a desktop is a unit of work. Right? It's a place where you go and you do a project that persists over days. What happened when this interface went to Apple and then to Microsoft is that they forgot about the workflow aspect. So you have this silly thing of people building up windows and collapsing them, building up windows, whereas what you really want is something that sustains over time. So if you look carefully up here, you can see the presentation that you've seen so far, and that is because I can have any number of sortings of these desktops, right? These desktops are like web pages. I can hand them around, except they're full-blown media with objects. They run in a browser because Squeak can be a plug-in, but I can also sort them. So if I want to come back to my Miracle Happen slide next, I can put it in like that and say, okay, and I'm going to call it the Intel November 27 talk. I can use these guys over and over again here. And so if I go now to the next slide, it's not the one that I had, but it's the one that I just put in there. See how simple this is? This is why PowerPoint is bad. PowerPoint is a thing that essentially neuters any powerful thing that you have done. It's an unpowerful point. You do this wonderful thing, and then you have to copy it into this weak thing in order to show it, but you can't show any of the dynamics, right? Whereas what you really want to do is just work in the thing, and some of them you're going to show and some of them you aren't going to show. Okay, here's another idea, and again using the children's programming, and this is just a little salmon here following a brightness gradient. You can read the thing. Fish is always going 4 by 5. The last seen thing is greater than the brightness under the fish. So I'm plotting what the fish is doing over here. If it's yes, keep on going straight. If it's no, just turn randomly. And so the wonderful thing is that this fish will eventually wind its way up there, and every living thing has this little algorithm built into it. And evolution has this algorithm built into it. This is what evolution actually does. It doesn't do anything more than this. Then the fun thing is, so having done such a simple little hill climbing thing, then if you have a particle system that is programmed the same way, you can do something much more interesting here, but almost as easily. So these are a bunch of ants, and this field that the ants are on is actually 10,000 little patch computers that are handling the diffusing of the pheromones and the evaporation of them. Right? And so even on this little laptop that I have, we can do 1 million particles at 10 frames a second, okay, from these tiny, simple little programs. I think most of you are aware that TEC is an example of a system that is able to do a very, very good job of solving certain kinds of constraints for dealing with these. And so this metaphor is spoken about in this paper as particle field programming. So just a zillion things, like sending messages in an object-oriented language is one of these things. You can think of this as a tuple space for Linda if you want. Right? There's just a zillion things where you want to be able to have an environment. And one of the differences between this children's environment and, say, Squeak or Java is that the objects in here can all see each other because they're in the same and they're actually situated. We don't use Lisp sharing. Smalltalk uses Lisp sharing, but the eToy system doesn't. So everybody knows where they are. Okay, so here's an example of particle field programming. So here's a little text paragraph. So I'm just getting it to justify itself. Everybody has done this program, but maybe not this way. This is the entire text editor shown on the screen here. And I'll reveal what's going on here by letting these guys loose. Okay, so each one of these is a little guy, one of those ants. And so the formatting, if I tell them to just wander back, you can see them following the leader. If I tell them to hop back, then they stop. If I tell them to snap back, they snap back. And now they do that thing in between the frame time. And in this system, the process switching and the message passing are the same speed. Right, so it actually doesn't cost you to have 200,000 processes in this system. You can just use them. And all of a sudden, you wind up with these extremely simple, like this is all you need to do the formatting. And this is all you need to do the selection. So if I draw through, each of these guys is actually looking out to see where the thing is, and the editing for doing it. So let's see. This is a Japanese keyboard, so I have to be careful here. Maybe this one. Nope. That one, okay.
Could the spell check be put on the screen too?
The spell check is usually done by having lots of examples. Right? I don't know of any algorithm that understands English intrinsically, so I'm not sure what your question is, but sure, you mean the thing to check to see whether you're at some interesting Hamming distance from the thing. I don't know because we haven't done it. So I'm just taking Don Knuth's escape route here, but it better be because this system, in order to fit into 20,000 lines, all of this stuff has to be done in this kind of Model T code. Because the basic idea here is that you should be able to, I'll give you a little example. So here's a simple animation program, and the kid just made different examples and wrote this two-liner. And the movies are essentially animations. So here's a movie for dropping a ball in this gravity thing, and that is exactly the same code at the end user level. And this movie is the So this movie has exactly the same two-liner, but there are things in between. So this thing is actually fetching the frames off the disk. It's doing an MPEG decoding of them and so forth. But the master code for what the movie is and what the user interface is exactly the same. And I won't. Okay, and I've already showed you this, but this is kind of that ANTS thing done as desktop publishing. Or maybe not. So the text runs around, and so now it has, this is a harder task because it has to do the anti-aliasing on the text. Okay, now of course the kid's system wasn't actually made to do this, but now let's just take maybe one example from down here as maybe the last actual example. Here's one that I already mentioned, is that you should be able to replace any wiring system with an Ethernet, and I believe you should be able to replace the hundreds of different ways that messages are sent to each other in operating systems by also something like that. That is, you should be able to replace an operating system with an internet internally. And another thing that is kind of annoying, it goes all the way back to Tony Hoare and Dijkstra, is the idea of using semaphores and monitors and stuff like that. And the problem with those is that they cause various kinds of bottlenecks and lockup. And at the very same time when that stuff was being done, the Simula guys and John McCarthy separately were doing a much better way of thinking about this stuff, and that is to run your computations in pseudo-time. When you run in pseudo-time, there are no race conditions that are not detectable, because you're basically labeling every state. And you're essentially only advancing the pseudo-time clock when you're not doing any computation. I will not go too much further, but a very interesting example of this is Dave Reed's thesis. Reed is the guy who's the slash in TCP/IP. He was the guy who suggested separating them, and his thesis was about how to distribute computations over the internet. Right, so the idea is there are just so many examples where you have to essentially clone an object that you want to remain logically distinct. So you essentially have the dynamic version of atomic transactions on distributed databases, except you've got objects. And so Reed's thesis was one of the first schemes that allows you to do that kind of coordination safely. And it actually works well enough so that you can do something that appears to be real time to the end users. Okay, and I just refer you to that. We have done 2 versions of this, and if you're interested, you can go look at Croquet on the internet. So this is essentially a model of computation where time is actually part of the model. It's not something that happens to you from the outside. It's something that you are actually controlling. Okay, so this is Ian Piamarta's work, and I suggest having him invited if you're interested in this stuff. This is pretty neat. I think of this as good old-time computer science because it's something that was big in the late 60s, which was how can you do extensible languages from tiny kernels and still have them run very well. So we can describe the system as a little golden box. And some of the people in this room, I'm sure, have done things kind of like it. So, for example, one of these pages of the couple hundred lines of code here looks kind of like a BNF, and it has patterns that are translatable. And so 150 lines or so into the golden box makes a JavaScript or Python or Prolog or pretty much any of the languages today. The JavaScript one runs about 20 times as fast as the one in the browser. And that's because the golden box generates machine code for a wide variety of platforms, not interpreters. Okay, and so this is a key part of this thing, is you'd like to have something that has all of these wonderful self-reflective properties, but is still able to compile fast code. And then the other trick that the golden box can do is 1,000 lines of code put into the golden box makes another golden box. So in fact, in a week, you can experiment with 3 or 4 programming languages, change the golden box, and the next week you have a different golden box and you have a different set of experiments. And we've been doing this starting in the summer, and as Mick Jagger might say, it's only math and science. Basically, this is something that many of the graduate students I've run into just have never had the experience of bootstrapping from scratch, because they're supposed to learn Java, they're supposed to learn all of them. You would think they were going to some sort of trade school rather than learning how to do real computing. Actually, an interesting example of that, just show you. So this is about 300 lines of code. So we're going to make a JavaScript from scratch and then give it a Tetris program. So it makes this little engine. I don't know why. Graduate students are a lot faster than I am. But you get the idea. So that's like about 350 lines of code to do that. And part of the experiments down here are just to do lots of these, to try and understand what the best balance, because we actually can't spend a lot of time and a lot of lines of code down at this end and be successful in this project. So the next project in the golden box is to do TCP/IP, because it might sound kind of weird, but if you think of TCP/IP, it's kind of a parsing and pattern matching problem if you were to look at it from that. Like you could think of it as kind of a pipeline process with non-determinism in there in an interesting way. And so we think it can be done in around 200 lines of code and actually run fast enough to fulfill what TCP/IP has to do on the network. And that will be a very good test of some of these ideas. Okay, so the approach here is to say that there's really 2 things that have gotten smashed into one in computing. And actually there's a psychology that has arisen because of it. So my first machine in 1961 was an 8K byte 1401. And in those days, the number one thing that a programmer had to be able to do was to cope. And I would claim that over those 45 years, that has pretty much stayed constant. That a large part of what it means to be a programmer is to be able to cope with what's there, because kind of that's what they're paying you for. Problem is, that's not what they're paying graduate students for. Right? Graduate students need to say, no, I'm not going to cope with this. This is shit. I'm going to do this, this, and this. But in fact, we hire people who have a huge background in programming. And so they're willing to show how much pain they can take when you give them some system. And they tend to just add on to that system instead of saying, this is shit. So that's a huge problem. So one of the things that this is one of the most important parts of the system is to completely separate out the meanings. And the meanings are not going to be expressed in terms of unit tests or just predicates. The meanings have to be expressed in terms of a runnable code, sufficient enough to get the entire system running. But the meanings are going to be completely separated from the optimizations. Completely. So that any set of optimizations can be turned off while the system is running and it will still run. So Model T here, I grew up with Model T on a farm in Massachusetts. The reason they were still there is you could not really destroy a Model T. You would have to grenade it or something because it was made out of cast iron, and the farms all had little blacksmithy things and only had about 350 main parts and about 1,000 screws and other things. And basically a 12 or 13-year-old could take it apart on the floor of a barn, do something to it, and put it back together over a weekend. And yet, it was a completely real automobile. So it's just, I wish people had that experience. And the reason I put this dime here is to remind me to say that the spark gap on the Model T was set by the thickness of a dime. And when they asked Henry Ford, why did he do that? He says, well, people lose gauges, but they usually have a dime on them. Can you imagine any automobile today being done that way? It's like you have to put on a radiation suit to open the hood of them. So the premise here is that the actual meaning, the meaningful semantics separated out from the pragmatics is actually tiny. That's what my intuition says. There's hardly any content in these millions of lines of code. And that combined with extreme late binding, right? So if you're working in an early binding system, you're doing something, but you're going to have a hard time doing all the experiments that you need, and you're going to have a hard time taking the important things you've learned when you've gotten this far and being able to put them back in here. So this leads to sort of the first and only system syndrome, and then people feed that system rather than throwing it away. And I think it's vital, given that we don't understand how to do computer science or software engineering, to make everything late bound. Okay, just a couple. Okay, so the other thing that's exciting, and it's happening right here at Berkeley, and some of you may be familiar with Dave Patterson's RAMP project here. Anybody? So Dave is a very cool guy. And Chuck Thacker here is an even cooler guy in a way, because he was responsible for all of the hardware architectures that we had at Xerox PARC. He would just make these machines. About every 18 months, he would make a new machine for us. And we had a little manufacturing facility, so about 2,000 of these Altos were actually made by us in the 70s. So we could hand them out to everybody. And Chuck is in the middle of taking the next field programmable gate array technology and making an Alto for 2007. Right? An Alto being defined as 2 cubic feet of the fastest hardware on the planet. And it gives you two things. It gives you the ability to do a lot of things without having to optimize. or it gives you the chance to actually do a program as it would be done 10 years in the future. Right? Then you would do some optimization. So both of those things obtained at Xerox PARC, and this machine was at least more responsible, I think, for our success than most of our good ideas. The fact that we had that thing, it just completely changed the dynamic of what we were willing to try. And trying in both directions, we got a lot of insights both ways. So here's the sermon here is that we have to be conscious that our nervous system is internalizing what's constant in our environment as normal. And as explorative scientists and designers, we cannot tolerate that. So the number one thing is just to be aware of whatever you think is normal is probably bad for you. Right? Just getting sensitized to it, because it's the basic attitude in science. Common sense dominated for 200,000 years. 400 years ago, people started finding ways around what was wrong with human common sense. And the same thing is in computing today, is that the common sense of most of the people who are coping with all of the stuff that's out there today is completely blinding them to what the actual possibilities are. I think I'll just, these are a couple of statistics about this system done dynamically. So I'm just asking it how many, what size is all the code in the system of this thing that I've shown you. It's about 3.5 megabytes. And how many methods are there? And about 60,000, which is huge. But the average number of bytes per method is only 59, so that's not bad. So they're tiny little things. 230,000 lines of code in the system. And the total number of objects in here, because this is a dynamic system, I can actually ask it to count all the objects in the system, including all the integers in it right now. So that's always an interesting number. So just a little less than 5 million dynamic objects in the system, going on, with the same architecture going all the way down to where there isn't an operating system, but where what an operating system does. So this is kind of a sloppy example that you can do something interesting in a few 100,000 lines of code that covers large parts of what we think of as personal computing, and I think we can go a factor of 10 smaller. And I invite any of you who are interested to contact me, and we have money for internships and faculty consulting, et cetera, and it's going to take a fair number of people who are interested in solving these difficult problems to make the results of this project interesting. Thank you very much. Any questions? It is preposterous, so let's get past that. Yes?
So it's 10 times smaller than the current system. It only take one person.
Well,
Just 10 times.
that's sure one person with a factor of 10 more IQ than I have. Absolutely. Although we have a graduate student who has a factor of 5 more IQ than I have. So, yeah, 2. We just really need one more graduate student. Exactly. Yes.
Are you familiar with what Google's doing with their MapReduce paradigm and their Sawzall language? Is that
Well, it's
similarity?
basically although Google is, I've been talking to Peter Norvig over there off and on, trying to get them interested. We don't need funding from them, thank goodness. But I've been trying to get them interested in some of this higher level stuff. Most of the stuff that they're doing over there is trying to make the executables smaller. but I'm not aware of of trying for really high levels of expression. But maybe you know something I don't. But I go over there every once in a while, every couple of months or so, and talk to them about what they're doing. It's interesting that if you look at the web programming, that the actual programming languages are, except for the fact that they lack depth, are rather similar to any dynamic language, the scripting languages like JavaScript and Python. But what is lacking in there terribly is the environment. In the browser, it's the DOM, which is just really a god-awful mess. It doesn't have any power, and the JavaScript, which you can get to, is not strong enough to allow you to supply your own primitives to that. Like, you should be able to override stuff that's in the DOM. Like, if you don't like the way their canvas goes, you should be able to take JavaScript running 50 times faster and write a better canvas in there, but you can't, because they just aren't. The scripting languages are thought of as add-ons onto some thing that was originally written in C++ or some other kind of thing. So the architecture is actually walled off, and it reminds me of like experiments in radioactive chemistry, where there's that dangerous stuff behind the lead wall, and you're over here with the Waldos pouring things. Whereas if you take something that isn't reference to our own work in the past, but you take something that we looked on with some admiration, the Lisp machine that the MIT AI lab did, and then there's a Lisp machine company. That was an example of a higher level architecture done from the bottom up to the top, or top down to the bottom. So the hardware was there to run the programming language efficiently, and so that every single part of that system could be criticized by some programmer, and you could override it with something of your own. I mean, even Simula had it. Simula had this idea of virtual procedures, and even though it was an early bound language, a virtual procedure, if you mark some procedure in a superclass virtual, and you subclassed it and supplied a procedure with that name, it would actually also be called up in the superclass. So you could have a mediocre sort program up in the superclass, you could write a better sort program, and the whole system would use that better sort program, not just your subclass. Right? And that's done dynamically in the small talks. But basically all of those things are saying that in the end you need to be able to have your cake and eat it too. You have to have perfect safety. And one of the ways of doing that is to notice how difficult it is to really crash the internet. Right? It's only with some computer program. The internet can't really be crashed. You can slow it down. But the only crashes that ever happen are some bad piece of code in somebody else's operating system deciding to execute some perfectly innocent message they were sent. Right? So if you think about the internet, it's a pure messaging environment that does not have in it the ability to crash itself. That was deliberate by those guys. But then you have this possibility. Once you have that, then you can actually safely override anything with something better. So I don't want to criticize the way programming is done on the net, but I wish they would do it a different way. Basically, it's like a pop culture trying to reinvent Bach. And it's just hard to do it that way. Because Bach was a one of a time. You're better off reading about Bach and Newton rather than trying to recapitulate what they did. So I think that's the big problem there. Yes?
Yeah, so in what you are saying about starting from the down to the middle, you have already invented Smalltalk, and there are like object-oriented systems available and all that stuff. Do you mean
Because in the end, the programmers succumb to the temptation of using the library and using this and using the other thing. And it wasn't supposed to happen with Squeak. I actually got blood oaths from some of the systems people who we worked on with that thing. But in the end, when the shit hit the fan, they just wouldn't get rid of it because it was too useful. And that's why I gave that funny little demo, because I haven't actually run a demo from a command line interface since like the early 70s. But yeah, we decided, and that's why EMP-MARTA stuff is important just for morale. And we just decided that even though it's going to be inconvenient, psychologically, it's going to be critical for us to believe that we don't have to make a big scaffolding and small talk and then promise to ourselves that we're going to get rid of it later. And we're absolutely going to build the stuff from the raw bits. And Ian's stuff generates machine code, and that's the machine code we're going to live with as we go on there. And of course, we have to, right away, we have to make some sort of interactive development environment for it, because we absolutely don't want to be pushing text files into the thing. But as soon as we do that, we've actually started down the pathway of making commitments too early. Interactive development environments are actually a fair amount of work, and you need them early. So once you've done that, all of a sudden you've set the tone of what one part of the architecture is going to be, and then try and get any programmer to give up that thing. So a lot of the logistics on this thing are basically, the plans that I draw are plans that for the first year, 2007, we basically are going to have 5 or 6 parallel strands of just doing throwaway experiments. Because we think we understand how the top end works in this thing. That's the thing we understand the most of this single object model at the sort of in the end user space and how you get everything out of it. And getting the bottom to a place where we can get into that yellow ellipse without having made too many commitments already at the top is basically the trick on this project. We have to get ourselves into a place where we can do serious throwaway experiments with very high-level constructs that are actually going to take a fair amount of work to do. So it's kind of, and basically when people join the project, I explain the deal here. This is not just a technical project. It's actually dealing with psychological difficulties that we all have as computer scientists and designers. And, thank goodness. And NSF gave us an incredible gift here, because this is the first funding I've gotten since 1990 that didn't have a lot of side conditions on it. They just really did fund this thing, and I found another $1 million a year for 5 years to make this the size project it can be, and there's just nobody waiting for us to get done on this thing, right? So it's like Xerox PARC, except we don't have Butler Lamson down the hall to tell us why we're doing it all wrong, right? And I miss him terribly because Butler had an interesting way of being right in the most important way you can be, even when we went against him. The fact that he was critical in the particular way he was helped us thinking about why we really didn't want to do it that way, right? Because he's just incredibly sharp. So, so it's an interesting deal of trying to find. In fact, I've been talking to the UCLA Computer Science Department, where I'm on the faculty there, but they have this paper mill for both graduate students and professors that is just outrageous. It's outrageous. Nobody can do any real work because they have to write so many papers. And when I went to graduate school, you basically only had to do your PhD thesis, and it was supposed to be good. But they didn't waste anybody's effort with little things along the way, because they just divert focus. So we're getting actually a lot of cooperation. The computer science department is cooperating. We have one of the professors roped in. See, one of the interesting ideas in this system is typing is big today. But of course, what you need typing for is something completely different in a system like this. And most of the typing results are not at all interesting. But there's a thing that's like a super type, which is to think of an object or a method being able to characterize what that object or method needs in its environment in order to actually run. Right? So one of the things that's proposed in there is the idea that instead of worrying about typing on variables, we should be worrying about typing meaning. And in fact, any object we really care about, we should write a stub environment that allows the object to run just in that environment standalone. Right? And you can think of that as being a simulation of its typeness, even if you don't know what it is logically. And when you take that object and put it in a dynamic environment, then it may find some of the things it needs in the environment, but the stubs also supply the defaults now that may or may not be there. Right? So this is a late binding idea for trying to guarantee that the meaningful stuff that you've said over here stays meaningful over here, which is kind of what typing is about. It's just that it's not that interesting to have it be an integer or a string and a variable. That just doesn't cut it as far as what you're really trying to deal with. So that is a really interesting theoretical problem, but it's also an interesting practical one of how can you make it easy for the program. So you should be able to use something like type inference to try and start building this external model. You should be able to present it in a user interface to help the programmer. Because maybe instead of maybe there's a function out there, but maybe you just give it some typical values to start off with. So now it starts looking like an AI program. Like one of Doug Lennett's automated mathematician programs, or Eurisco, that goes around gathering evidence before it tries to make a picture of the function. Right, so that's one of the dozen things in there that we think really needs to be done. Another one is set of support. So AI has this idea of truth maintenance, but no system I know of actually has truth maintenance of a method. Same idea, right? Some systems programmer changes something over here, and all of a sudden your method, which was running perfectly well, is not running so well anymore, even though it passed all the unit tests over here. Right? That just can't be allowed to do it, but nobody knows how to deal with that problem. But it's clearly part of what software engineering has to be able to deal with. So it's akin to being able to have some sensitivity to the signal levels that are actually being sent you in an IC. So there's a lot of interesting things. At least we find this project very interesting, and we didn't expect to get funded, and we just actually got our first infusion of money a few days ago from them, so I think it's real. Yes?
Could you explain further what you meant by one golden box leading to another?
Yeah, well, the golden box, I've tried a lot of different ways of explain, but basically so if you could, the golden box actually has two models that are intertwined in each other. And the simplest way of thinking about it is if you go back to that one half-page Lisp in itself, so you can't run that, right? Because there's no energy coming in. So it's just meta-circular. And so to run it, you have to actually sneak in some computation somewhere. And one of the things you can do there, and it's a really good exercise to do it, is to try and figure out how you could use something very much like what McCarthy wrote, but instead of describing an interpreter, what the thing does is to emit machine code. some of the early Lisp compilers back in the 60s did just that, because they realized, oh yeah, this thing is chugging it along there, and the main difference between compilation and interpretation is that when I'm compiling, I have to generate code that will make that result that I would expect to get from the interpreter. So if you do that really carefully, you wind up with this thing that is essentially a compiler for things that are of the power of Lisp, that are about the size of that half page of code, but they actually generate machine code. That's just a revelation, because it's right there. And you turn the crank on it, and it starts making new versions of itself, right? Because it's written in itself. So the golden box is, 30 years of sophistication on top of that for methods. And then, kind of orthogonally, it has a meta model for what objects mean. And by the way, that system is called Albert in here, and there is a paper online that you can read that tries to explain just what this thing does. So what that slide meant is that the golden box is something that will take a description of some correspondence of some form and assign meanings to it, and then it will compile code from that. That's what the golden box does. And the size of the golden box itself is only 1,000 lines of code. And it's in exactly the same form as what you put in there to get JavaScript. The JavaScript is only like 150 lines of code. Golden Box has many other things, and it uses the pattern matcher for also doing register allocation and stuff like that. It's pretty sophisticated, but still small. So it's basically 1,000 lines that generates a complete kernel that can generate other things out of it. That's a very 60s kind of thing. The first Smalltalk at Xerox PARC was done very much like that, Smalltalk 72. But the difference between then and now is that this thing has just had a lot more thought put into it than what we knew how to do back then. And this guy, Ian Piamarta, who got his PhD at Manchester, is a bit of a genius, I think. So the golden box is actually philosophically interesting also. But it's not a secret. I mean, it's just, there are papers being written about it. But it has this interesting thing that because it doesn't take much to specify a language, you can do it kind of in an afternoon and do a bunch of experiments. You can do a couple of languages every couple of days and try out various kinds of schemes on the thing. And that usually tells you something about what the golden box is or is not doing for you. But then you can go and modify those 1,000 lines and shove it through the golden box. You get a new golden box. And so you just, at some point, you don't take such a draconian measure on the thing. But for experiments, it's wonderful because it's actually think about it. I mean, we have the golden box itself up on the wall. We print it out and put it up on the wall so we can just look at it. Because it's whatever 50 into 1,000 is. It's like 20 pages of code or so. So it's a contemplatable kind of thing. It has a garbage collector in it. It has a bunch of different things in there that allow it to make a little environment. It's just a better one than we did for Smalltalk 72. But it's similar. The biggest program the Alto could handle when it was first done was 20 pages of Smalltalk. And we were doing, complete windowing systems and modeless editors and everything else on the thing, in part because it could only hold 20 pages of code. So we had to think about what the meaning of those 20 pages could actually be. And part of it is just necessity. It's like the $100 laptop. I'm going to try and get some for both UCLA and Berkeley, if I can get them away from Nicholas. But all of the ones right now are slated for the third world. But it is just a great machine to give to a graduate student because it's about a factor of 5 to 10 slower than today's laptops. And yet, it's a factor of 20 or 30 times faster than the Alto was. Right? It's $100, and any computer person should be able to do something on this machine. And it just changes the scale of what you're going to try and do. And basically, I think for good computer people, it just immediately gets them thinking higher level thoughts. Because they know instinctively that this thing that's this big is really this big if they could just figure out what it is mathematically. Thank you very much. Thank you.